let's move on. And now let's slightly switch gears and talk about uncertainty and its propagation. Okay? So we have this measurement error, and last time I told you guys we always have error in any measurement, right? And so the error is defined by measured value minus the true value. And here we would like to focus on this measurement value. So the error, like we did, is defined by this relationship, and we would like to focus on this measurement stuff. So uncertainty is a quantification of the doubt about your measurement result. And it's a range that likely contains the true value. So error is your measurement versus true value, okay? And uncertainty is about your measurement. All right? And, well, we use this measurement as like a general term here, but if you are really into this field, people have these in like two categories. One is called readings, and the other is called measurement. Okay? And readings are the case where reference or the 0 point is already provided or it's calibrated for you. And measurement is you are the one who needs to line up and read the values, even for the 0 point. Okay? So how about we think about these two cases here. Again, there's this guy, and he has that annual health checkup, and then he goes there and then measures his height using this machine, and boom, it comes down, and then boom, it measures it. Okay? And it tells us, hey, your height is here. The other case is you go to have a new suit, and then the tailor there, that person is measuring your height using that fancy ruler. Okay? So in this case, we're not sure whether this is referenced correctly or not. Okay? Get it? The slight difference between these two? And let's say we have a digital scale. Okay? This guy, we just trust that thing. This guy is referenced or calibrated correctly. But when you go on a scale like that, then you need to do what? You need to calibrate it, and you need to read it, right? So you're doing this twice. This is something you are involved in there. So we can call these as reading and these as measurement, like that. And I just use an example of, measuring height and measuring weight or things like that. There can be other devices like thermometer or, other sensors, and it has their own contexts. So I can't talk about all the cases, but the rule of thumb here is the readings are the case where it is calibrated already for you, and measurement involves you to calibrate and you to measure, you to calibrate and you to measure. Okay? Does that make sense? Simple. And let's first talk about the case here. And the readings, there's no need to line up. And the uncertainty in this case is same as half of the resolution. So for example, here the uncertainty is 1/2 of a centimeter. Well, these were all in centimeters. So your measurement, the minimum resolution we have is 1 centimeter here. So that was the resolution, and you have that one, and that's going to be the uncertainty for this case. Okay? On the other hand, if it was a measurement, then uncertainty is the resolution. So for example, here we have, 1 centimeter. That's this. And qualitatively, you can think, oh, there's uncertainty here and there's uncertainty there, so it's just that resolution, like half you have from here, half you have from there, so that's the uncertainty of your measurement. Okay? It's pretty simple. And now we would like to think about how we can express this uncertainty. So, for example, for this case, again, 175 is the reading we got, 0.0 plus and minus 0.5 centimeter. And the important thing is you need to match the decimal places of the measurement to the uncertainty. So what I mean is, it's like 175. That's the value you got, and you had 0.5 as your uncertainty. Then, technically speaking, this is wrong. It has to be 0.0. On the other hand, if we express the uncertainty for this case, it's going to be 175 plus minus 1 centimeter, because this one here has what? The decimal places to the ones, right? So we're not having that dot there. Does that make sense? Okay. And let's talk about, what if the measurement was digital, or the data acquisition method is not really clear? Then we just assume the resolution itself is one significant figure. Oh, my bad. Assume uncertainty is the one of the last significant figure there. So if there was whatever device and some voltage value was obtained as 2.25 volt, okay, you just borrowed a multimeter from your friend, and then it just gave you 2.25 when you measured something. Then the uncertainty in this case is going to be what? Anybody? Yes, it's going to be plus and minus 0.01 volt, like that. This is the last significant figure, and we just make it 1, and then you put it there. So if you measured something, or it gave us 15, and you don't know how it was measured, you just assume that's plus and minus 1 meter. If this is given, then what? It's going to be 0.1 plus and minus Fahrenheit, like that. Okay? These are all just definitions. And if something was measured multiple times, The uncertainty is going to be defined in two ways. So one case is people use one standard deviation as the uncertainty, and this is usually preferred in engineering. On the other hand, there are many cases where people just use 1/2 of the max value minus the min value. Okay? So, for example, let's say we had this multiple measurement of the weight of someone in the previous example. Okay? And if these were all just given, then one way to define the uncertainty is you find the standard deviation of this guy, and you just have plus and minus one standard deviation. That's your uncertainty. Or you can find the max value. Which one is the max here? This seems like the max. And then the smallest value is, I have 71 here, this one. So you can find the difference between these two and then and multiply 1/2. And that can also be used as the uncertainty. But oftentimes in engineering, this is preferred. Okay? All right, any questions up to here? We just talked about all the definitions here.